Hey there, everybody. Mr. Mark with you. In this video, we are going to go over, discuss, and then score the rotation for response question. And this is an example of a qualitative-quantitative translation question. So what the term qualitative-quantitative translation means is that you're expected to be able to translate a situation between descriptive, like words, responses, and then mathematical, like graphs and equations responses. So kind of one pro tip we're going to talk about right off the bat in answering these is you don't necessarily have to go in order and answer the question A, B, C, D. For a lot of people, it may be better to start with part C or D and then use that to help you with part A because you're talking about the same situation in a lot of cases. So if you're like, wait a minute, I didn't really get all that in part A, maybe if you did it on part C first, it would have helped you out with part A. So that's kind of a thing that we're going to kind of see here at the beginning of this question today. So in this question, we've got this wheel at the top of a ramp, and we're given the moment of inertia equation, and this thing is going to roll down without slipping to the bottom of this ramp. And we want it to be going as fast as possible when it reaches the bottom of the ramp, and we're supposed to check what things could be increased to cause it to have an increased velocity at the bottom of the ramp. So part A is worth 2 points. And we should have checked only the height, checking only the height, and then justifying it using energy conservation would be worth 1 point. So just that the energy that it starts with is gravitational potential energy, mgh. And the second point is for that being the only thing that is checked. So for checking nothing else, you would get a second point. Now, if you checked nothing, then you get nothing. You have to check at least height and explain in terms of energy conservation at the first point, and then have everything else unchecked in addition to that to get the second point. If you try to do some sort of explanation by saying that the increased height will allow it to speed up for longer with the same acceleration, then that would be an okay answer as well. That would get you the first point, but you still have to have everything else unchecked to get the second point. Okay, so part B depends on your answer to part A. In part B, we're asked, hey, here's an equation. Does it agree with your reasoning in part A? And so if you look at the equation, up there on the top of the equation is an H. So that equation says if H gets bigger, then V gets bigger. And so if we checked H up above, our answer should be yes, because it shows that increasing the height will increase the velocity, just as we said in part A. So you don't have to redo your work for part A. You just have to say that yes, it agrees with your reasoning in part A, because the equation shows more height means more velocity. Now, if you did not check H in part A, then you could still get full credit for this. Your answer would be no, and you would just have the inverse reasoning. This equation over here says increasing height makes velocity bigger, but your incorrect reasoning in A said differently. So depending on your answer to A will determine which of those you look at. So increasing the height in this equation does increase the velocity, then does that agree with your answer to part A? If your answer to part A was height increases the velocity, you should have checked yes. If not, you should have checked no. Okay, part C is now a student derives this equation right there without deriving the correct equation. So don't just rely on going, hey, here's what's right, this must be wrong. Explain how you can tell that that's not physically plausible, that it doesn't make physical sense. So the thing to key on in that equation is the fact that the radius of the wheel doesn't matter. The radius should not be in the equation for velocity. So if you did something to the fact that the radius is the thing that doesn't need to be in there, then you get 1 point. And that's really kind of the only thing that I could really clue in on that would be incorrect in that equation. Sometimes questions like these, there's several things wrong with the equation, and really you just need to pick out one of them. So choose the easiest one, obviously. But here there's only really that one thing. So the radius cancels out in the equation. You don't have to show that, just briefly explain means, hey, the radius of the wheel is not going to affect how fast it's going at the bottom. All right, part B. Now we replace the wheel with a solid cylindrical wheel with identical mass and radius, and then how would the speed of the cylinder compare to that of the original wheel? So we should have checked greater than. If we checked equal to, then we're not going to get any points on there, even though you may have some good physics still. There's not enough points to go around. If you checked less than, then you could potentially get a maximum of 2 points. So briefly explain your reasoning. Mine wasn't real brief, but here's the things you need to have. First of all, you indicate that the cylinder has less inertia than the wheel. You're really only going to get that point if you checked greater than up here. So if you checked less than or equal to, less than, you're not going to get that point in all likelihood. The second is to say that the cylinder is going to gain less rotational kinetic energy, or you could say that the original wheel would gain more rotational kinetic energy. So saying one thing and saying the inverse of that thing would be the same. And then since the total energy is the same, and we do need to mention something about the total energy being the same, then the cylinder is going to gain more translational kinetic energy and thus more velocity. So that third point on there is kind of two parts. One, starting with the same energy. Two, that means that the cylinder is going to have more translational kinetic energy and thus more velocity. If you check less than, then you might look at this. If you check less than, and then you just had the wrong idea about the moment of inertia, because it doesn't give you the equations, you just have to go, hey, the cylinder's got more mass closer to the center. It's going to be easier to turn a cylinder than a hoop wheel. The cylinder's got less inertia. So if you couldn't connect that dot, you can still get the last 2 points if you got them reversed. So you wouldn't get the first point if you said that the cylinder has more inertia, but you could say that the cylinder would have more rotational kinetic energy and thus less translational kinetic energy and get 2 out of the 3 points. So that first point is for kind of recognizing how the shape is going to affect this thing rolling down the ramp. All right, part E. It's getting long. In order to refine their understanding, they now take a rod and they fix it in the center, and then they launch clay spheres, which I think that's what these are supposed to be, so that they hit the right edge of the rod, and then afterwards they rotate with angular velocity omega. And we're given the moment of inertia of the clay with respect to the rod. So first of all, we're asked which of those things are conserved in the experiment. So we should have checked angular momentum and not linear momentum. So linear momentum is not conserved because there's an external force, but that external force does not exert a torque. And so linear momentum is not conserved because of an external force. It is angular momentum is conserved because there's no external torque. So those are the 2 things you have to mention to get this first point. And then the second point is for not checking energy with some sort of explanation. You can say that the collision is inelastic, sticking together, or somehow the energy is lost to thermal energy. So really just recognizing that since you were told it's an inelastic collision, you know the energy has to be lost. So part I is relatively straightforward. Part double I is not. Double I is derive an expression for the moment of inertia of the rod in terms of the given quantities of fundamental constants. So first of all, we kind of have to recognize that angular momentum is conserved. That's our starting point here. So the momentum of just our little clay spheres before the collision, so that's like right there, is equal to the combined momentums after the collision. So that would be the sphere after it sticks to the rod plus the angular momentum of the rod. So 1 point for having an equation that looks like this. The angular momentum of the spheres before the collision equals the sum of the angular momentums after the collision. Then we're going to do L equals I omega for both the sphere and the rod. So over here, that's going to look like that, just mv times r. That would be our third point, by the way, mv r. And then our r is L over 2. And then do an I omega and I omega. So I, for the spheres, is given to us. That's the 1/2 ml squared right there. And then I for the rod is what we're solving for. I think I switched my terms around going from here to here. This term right here is the rod, and this term right here is the sphere. I think I switched my terms around going from this step to this step. Sorry about that. So once we have those things substituted in, we're kind of done scoring it. The right answer is this. You could simplify it, but I'd rather you not. I'd just leave it like that. But as long as you've got the correct starting equation, that's 1 point. You've done the momentum of the system somehow is mvl over 2. That's the second point. And then L equals I omega plus I omega for both the sphere and the rod. That's 3. There's your 3 points. We're done scoring. So in other words, if you made an algebra mistake, after that, we're not going to worry about it. If all you have is the correct answer, like if this is literally all that you writ, you get this many points. You got to have your work because it's a derived expression. Now it is, as I'm currently recording this, 2020, which means you're probably not likely to have a derive an expression equation on your AP exam this year in 2020 because it's all online and all the questions are designed to be answered with a keyboard. But I can think of a couple ways that they might test this skill while still having it be online. For example, they might say, write the starting point to the equation. Just show me where you would start, like write but do not solve kind of question. So they may ask you just to write that. They may give you something that looks like this with a mistake in it and say, in which step is there a mistake and what do they need to do to fix the mistake? So I'm looking at this work, all right, could I tell where I made a mistake and then explain why? So those are kind of things that can be answered with a keyboard that rely on you being able to derive an expression for something in terms of other things. So it's still worth your time, even in 2020 when we have an online AP exam to take, to be able to do this. The more that we can do this, the more fair will be for those kind of questions that they're going to ask. Okay, so that is the rotation FRQ, the first qualitative-quantitative translation question. There'll be many more to come. If you have a question, follow-up based on the scoring, please let me know. Shoot me an email or a classroom comment, and I'll be happy to help you out. Otherwise, go ahead and score yours to the best of your ability. And again, if you have questions, please let me know. Till next time, ta-ta.